Hi everyone, good to be with you. My name is John, and remember, this is Learn Extra Physical Sciences Paper 1, and we want to just make sure that you're polished and ready to go, that paper that you're going to be writing tomorrow, that you're absolutely calm for, and that you're ready to give of your very best. So if you've got any last minute questions, please phone us or send us an email. We'll give you those details right now. The email address is info@learnextra.co.za, and the phone number that you can dial us is 0861 058 262. Now, we've got people standing by to take your calls, and we'll make sure they go into an answering system. We'll try and answer as many of those calls as possible, so get dialing straight away. Now, of course, the other thing that I want to let you know about, last minute practice is always important with science. So we've made an arrangement that you can get extra questions on your mobile phone. So remember that we did that in the last session of live. We've got the QuizMax platform available. Let me remind you about that. Here we go. For paper 1, we're going to go to the QuizMax platform, which you will find over here. You can test yourself on a number of sections: mechanics, wave, sound and light, as well as electricity and magnetism. There are a number of questions. You go to this website. You can do it on a PC or on your mobile phone, www.quizmax.net. On your cell phone, use Opera Mini as the application to get that. It doesn't cost a lot. It's a very reasonable way to get some revision done. A few cents and you can log into a whole series of questions. So make sure you go and visit that website on your phone. You don't need a high-end phone either. It works on even most standard phones that have got internet connectivity. Right now, what we've got going is one of those questions. I want to take you through it because a lot of you have tried this question during the day and the results haven't been so good. So let's see if we can improve the results during this session. Check it out for yourself and let's make sure that we can improve it. I'm going to show you what the question is, even if you haven't gone on to QuizMax. Here it is. It says a ball is thrown perpendicularly into the air. So let's just stop and think about what that means. If I throw a ball perpendicular, that means at an angle of 90 degrees. Perpendicular, you need to know, is a special word meaning 90 degrees. And so that means it can't be thrown down if somebody's standing on the earth. It's thrown perpendicularly, meaning, another way of saying this, it's thrown up vertically into the air. Up or vertically into the air. There we go. And reaches its maximum height. Now remember, maximum height is very important. That is a key point. It reaches its maximum height. Here's some key information after 4 seconds. Remember that they've given you some very important information. What do you know happens at maximum height? Think about it. Make sure you've got all the detail of what's happening at maximum height. We know that happens after 4 seconds. If we choose down, very important idea here. If we choose down as our positive reference direction, so we're going to say when this object falls down, it's moving in the positive direction. So let's just sketch quickly. So we've got a picture of this. We've got the person standing here. The ball is thrown vertically up, and after 4 seconds, it reaches its maximum height. Now we're going to say going down is the positive direction. Okay? What next does it ask us next? What information does it give us? The velocity and acceleration of the ball can, after 5 seconds, 5 seconds from the start, don't think it's 5 seconds from the maximum, total distance of 5 seconds, can be represented respectively in the order. So we're going to look at, first of all, velocity, then acceleration. And here are the options. Option A tells us that in meters per second, it's minus 9,8. Acceleration in meters per second to the minus 2 is plus 9,8. Option B, plus 9,8, plus 9,8. C, plus 9,8, minus 9,8. And D gives you the values of both negative 9,8. One is velocity, one is acceleration. Take note of the units. It's very important that that will give you a clue as well. Okay, so that's a question. We're going to try and see if you can improve the score on that question. Use your cell phone during the break, check it out, see if you can find the right answer. And after a little while, we'll go over this question to make sure that you've got the concepts all sorted out. Okay, that's an introduction now. We're going to take a short break now, and after that we're going to dive into some questions and some things that you need to keep your head on and on top of your mind as you go into tomorrow's exam. Okay, I'll be back after the short break. Remember, you can phone us on 0861 058 262. And you can also email us your questions at info@learnextra.co.za. But if you do send us an email, please include your phone contact number where we can return your call and we can phone you to find additional information about the question you want to ask, as well as ask you to be a listener as we go through the question. We can answer your question. Now, lots of people are phoning us, and we're trying to get as many of the questions as possible that everyone is asking. We're going to go to some calls very soon, but there are a few things that I just want to have a last minute recap of and make sure that you can improve your results if you pay attention to these principles. So when we're dealing with mechanics, what do we need to watch out for? In fact, this applies to all of physics. When you're dealing with physics, you need to watch some very basic things. And I want to give you some hints. So you might want to take take this as John's hints for today. These are hints to help you with physics. When you deal with a physics problem, so in physics, what are the problems that you need to watch? Let me change the color of that, because that's a very... right, so physics hints. Here we go. Here are some of the things that I like to do when I'm preparing for a physics exam. The first thing that I need to make sure of is I familiarize myself with the data sheet. So make sure that you know exactly what that data sheet looks like. Make sure that you understand where all the equations are. You don't need to learn all the equations. It's fine if you have learned them, but at least know where they are on the data sheet. And they're nice and neatly labeled for you, so you can reference them. When you're doing a question on mechanics, open your data sheet and make sure you've got mechanics data sheet right there with all the constants ready for you. Of course, it does help if you memorize them, but you don't have to depend on memorizing them. If you don't know them now, don't spend tonight trying to memorize them. Rather, make sure you know where they are on the data sheet so you can find that missing information. The second thing that I think is very important is you need to make sure that you have a very clear strategy, a problem-solving approach. So a problem-solving strategy. And included in that problem-solving strategy, as I work through questions, as I'm going to just now, you'll see we'll do certain things. So when you read the question, highlight the important information, extract the information from the question, draw a diagram to illustrate that information. You can read it in words, but translate it into a diagram. It often makes more sense. And then the next thing that I want to mention, and it's something that we all battle with. Sometimes even teachers make mistakes. And one of the common mistakes that I've made before is check your units. Check for SI units. Okay, in one of the previous live shows that we did make a mistake on not converting from kilometers to meters. And you can't divide, for example, by a velocity given the speed of light as 3 times 10 to the 8 meters per second. You can't divide and multiply with kilometers reading. You've got to change the kilometers into meters so it works out. So please watch for that. Make sure you use SI units, and it's best to do that right at the beginning. And then check your answer. Make sure that when you give your answer that you have your units as part of your answer. That is extremely important. You will lose a mark if you don't have units in your answer. You don't get a mark for putting your units in, but if you don't have your units, there's a deduction. The other thing that's important, you need to know what are the vector quantities. Things like force and electric field strength, momentum. Those are vectors. They need to have a direction, unless they say to you, we only want the magnitude. But if they say to you, find the force, indicate the direction. They say we want the velocity, we want the acceleration, give the direction, because it's a vector. So you must give direction with vector quantities. Okay, now the next thing that I want to say to you, very important in physics, understand the principles, understand the concepts, understand the laws. And if you get stuck, don't panic. Don't spend too long on the arithmetic. Rather make sure that you spend the right amount of time on the question and make sure that you go on to the next question, which might be easier marks. So I'm going to say the fourth thing to get really good marks at physics, you've got to use correct time management. And time management goes down to the selection of the question. Remember, you don't have to start answering your question with question number 1. You don't have to give question number 1 as your answer. Question number 4 is the first answer in your answer book. You're going to answer some questions, the short questions in the special sheets provided, but you don't have to start there. In your reading time, read through the question paper very carefully, and then make sure that you choose the question that you're most confident. Yes, I know that. I can get 100% for that question. That's the approach that I use. So manage your time very carefully. Don't spend too long on questions that don't have a lot of marks for them. It's better to move on to questions where you can score marks than to spend too much time on questions that you're not going to get right. And even on tricky calculations you might have got stuck, leave it. You're going to get 1 mark for the answer. Your thinking and your physics might be right up until that point, and you get credit for it. Okay, now we're going to go to a call very soon. We've got Tiani that sent us in a question, and I know he's a regular caller, so while we try and get him on the line, let's go to a short break, and the next question we'll look at is a question from Tiani. Right, see you soon. Right, welcome back. It's good to be with you. Make sure you call us. Get your questions in. We're ready to take some calls now. And Tiani was early this morning. He sent in an email. Remember that email address is info@learnextra.co.za, or you can phone us on 0861 058 262. Tiani, good afternoon.
Good afternoon.
How are you doing? Tiani?
Yes.
How are you doing?
I'm all good, in yourself?
Yeah, good. Have the exams gone well?
Yeah, they are going well.
Oh, they're very good. Now, how can we help you with your science this afternoon? What's the question you've got? I think it's a mechanics question that I've got here. Question 4 from the November 2009 paper. Is that right?
Yeah, that's right.
Okay, let's have a look at it, and then you can tell me where you're having some difficulty with it, okay? So,
Sir,
yes.
this happened to be the wrong question. The November 2009.
Yes. Okay, can we just do this one? Because I don't have the access to the other one straight as I'm talking to you.
Okay, no problem.
Okay,
yeah,
because there were two November 2009 papers, and I wasn't sure which one you were wanting, so I chose this one because that's the one that was used. I think you might be referring to the one that wasn't used. But let's just quickly go through this one. We'll do the other one a little later. Okay, so help me go through this, and let's see. It'll be a quick revision for you, I'm sure. So we're told a ball is released from a certain height. The velocity time graph below represents the motion. Let's just make sure that we've got the motion of the ball as it bounces vertically on the concrete floor. The interaction of the ball with the floor is negligible. The interaction time of the ball is negligible and thus can be ignored. Okay, so question 4.1 says, describe the changes, if any, in velocity and acceleration of the ball from 0 seconds to 0,4 seconds. Okay, so Tiani, where do we start with this?
I think this is the velocity time graph.
Okay, very good. So you've identified this is velocity time. So notice here, this is velocity
from rest.
And that's time. Okay, and we know that it's starting from rest because, and it was released from a certain height. What else do we know? So what's happening to the velocity? After 0,4, notice the time interval they gave us from 0 to 0. So we're looking at what's happening to the velocity between that point and that point, okay, in this time period. So we're looking at the change in velocity vertically over there, between there and there, as the time changes between there and there. Are we okay?
Yes, okay.
Okay, so what do we notice? What's happening? Well, clearly, the velocity is increasing. So the first thing we're going to say, I hope you agree with me, 4.1, velocity, now watch, increases from 0 meters per second, 0 meters, put the dot in the middle, -1, okay, to what? Now notice, we've got to read it from the graph. They like us to use the graph. They've given us the graph for a reason, not just to say it increases. They want you to say
4 meters per second.
So we've read off the graph. I'm very glad that you can see that. So we're going to say it's gone from 0 meters per second to 4 meters per second. Okay?
Yeah.
Okay. Now, Tiani, here's the yes.
Oh, I was just agreeing to what you were saying.
Okay, great. What's the second part of the question? Have we answered the whole question?
No. I think we have to also describe the acceleration.
Okay, very good. So let's remind everyone out there, acceleration, what we're going to be looking for when we're dealing with acceleration. Acceleration.
The gradient of the velocity time graph.
Correct. It's the change in velocity over change in time. And look what we've got here. Change in velocity 4 divided by 0,4.
Yeah, it's definitely an increase.
Is the acceleration increasing?
Yes.
No, the acceleration, look at this line. What's the gradient?
The gradient?
Yes, it's a straight line, isn't it?
Yeah.
So,
and it's an increasing straight line.
It's an increasing straight line. Well, it's increasing, and the increasing tells us that it is positive.
Yeah.
Okay? It tells us that it's positive. The value of the gradient isn't increasing, though. Okay? The gradient at this point here is the same as the gradient at that point there. Is the same as the gradient at that point.
Yeah, it is.
I hope you've got that. So we know that the acceleration is a constant value. Okay?
Yes.
Okay, it's not increasing. It's a positive value that is constant. And that's the important thing. We need to say describe the changes. So what changes there in acceleration? There's no change in acceleration. The acceleration remains constant. Now, they didn't really, well, at this point, they didn't ask you to do it, but we can do it just so that we can get a complete answer. Can you see, using this equation, delta V would be 4, and delta T is 0,4. What's 0,4 divided by 4? Well, let's look at the calculator. Equals 10. Okay?
10, yes.
So notice, and I've done this deliberately for this particular question, it's 10 meters per second per second. Now, what is the real value of the acceleration due to gravity? What's the value we must use in our equations? Normally.
We must use 9.8 meters per second.
Correct. But notice here they gave us a graph which had information on. Maybe this equipment wasn't that accurate. So that's why it comes out to 10. So to get my complete answer, they asked me for the change. What we're going to say is the acceleration is constant at 10 meters per second to the minus 2 downward.
Yes.
Okay? And that's what the positive sign indicated. That's what that positive value, or the reason that the gradient was lying at a slope going upwards. Okay? Because that's positive. Are you with me? I hope it's coming right across on the camera there. So we've got it very clear. Okay, so that's 4.1. I think we've made it clear there's no change in acceleration, but there is an increase in velocity. So 4.2, let's see what it tells us. It says without using equations of motion, so we can't use calculate the height from which the ball has been dropped initially. So what they're asking, this ball was dropped from a certain height, and we want to know how high it dropped from, but we can't use equations of motion. What's the other way of doing it?
We know that the distance can be given by the speed multiplied by the time.
Okay, but that would be using an equation of motion. So I would rather not use that. Look what I'm doing over here. What have they given me? They've given me a graph.
Yeah.
So how am I going to use this graph? So when they say without the equations of motion, they've got
to... we have to find the area. Isn't it?
That's right. Absolutely. So what we're going to do is we need to find the area between the horizontal axis and the line. Okay, the one that I'm shading in at the moment.
Yeah, that's the one.
Okay, so this triangle, we must find the area of the triangle. Now, the reason that works is velocity, meters per second, times seconds is going to give us meters. Do you see that?
Yes.
Meters per second times seconds gives us meters. So let's do it. We're going to find the area between the graph and the axis, and we're going to say the following. So let's get the right pen so you can see it. Let's do the area under the graph equals, what is it equal to? Half the base times the height, and that tells us half. Well, now the base was the time interval, wasn't it? And the time interval was 0,4 seconds, and the height, vertical height?
The height was 4 meters per second.
It was 4 meters per second, so we can multiply those two together. That gives us 2 times 0,4, which is going to give us 0,8 meters. Okay? Is that right?
Yes, I'm fine.
Okay, good. Let's look at the next part of the question. And we're told here, copy the set of axes into your answer book. Use the given velocity versus time graph of the motion of the ball to sketch the corresponding position time graph for the time interval 0 to 0,7 seconds. Okay? So what we need to do is use it over here, use this sort of thing. This is a bit small, so I'm going to sketch one a little bit bigger, but I just want to make sure that I've got the velocities right. So where I'm looking for zero velocity here. Let's just pick up these points. 0 over here. Okay? We've got 4 meters per second there. Now notice this one is at about negative, I think this is about -3 or so, okay? I can count up, it's just a little bit above that, so that's a -3, and that's the 0,7 mark that we're looking, and that's 0. So I've now worked out what the velocities were in each of those cases, so that we've got it very clear what we've got and where we're looking at. We're not looking at the whole graph, we're only looking at the time interval from 0 to 0,7.
7, yes.
Okay. So let's think about what that means, Tiani. If I were to drop the ball, okay?
Yeah.
Then I'm dropping it from 0,8 meters. The initial velocity is 0. Do you agree?
Yes.
Okay. So where is it going to reach?
Yes, I agree.
Where is it going to reach its maximum velocity? Where? Over here in the middle, or when it hits the floor?
When it hits the floor.
Okay, so we know that the maximum velocity is going to be when it hits the ground, and that's going to be a value of 4 meters per second. Do you agree? Okay, so it started somewhere a distance of 0 or a displacement of 0,8. The position was 0,8 meters above the floor.
Yeah.
We normally take the floor, the earth, as the 0 point. Okay, you with that?
Yeah. Yes, I'm with that.
So we're going to start at 0,8 above the floor. It's going to hit the floor at this time, 0,4 seconds. And then what's it going to do? What happens at this point? Notice there's a change in direction.
Yeah.
You see that? So now it was positive, it's now negative. So what's happening? Change in direction. Look what happens.
It goes up.
It starts to go up. But notice it gets to 0 again, doesn't it? It gets to 0. So it reaches its maximum height at this point here. It reaches its maximum height at this point, and it has 0 velocity there at 0,7 seconds. So what we've got to recognize is this object is experiencing what force? It's experiencing the force of the Earth pulling down on it. And that is an acceleration, a constant acceleration. Are you with that?
Yes.
Okay.
Yes, I'm with that.
So let's draw the graph now. Constant acceleration means that initially it's going to I've only got a few minutes left, so I'm going to just sketch this very quickly. I'm going to put in the critical points, 0,4, 0,7. And over here was 0,8. Now, Tiani, the last thing that we need to do just very quickly is work out this. 0,4 to 0,7 is 3. Do you agree with that? 0,3. From 0,4 to 0,7, 0,3. Do you agree? Okay. And from 0,4, this time interval, 0,4 to 0,7, 0,3 seconds. Tiani?
You want me to calculate the height?
I'm wanting to calculate the height. That's right. So in the same way as I did before, I want to get this height. So I'm now working 0,3 times 3. That gives
0,45.
Is it? No, but this goes to 0,7. This was 0,7 over there, and this is 0,3. So 3 times 3, isn't that 9? Okay?
It is.
Okay. Do you want me to check it? So just quickly. So if I go 0.3 times 3, I'm going to get 0,9. Are you happy with that?
Sir, but I think we have to halve it because we're calculating the area.
Oh,
of the
that's
triangle.
very good. You see, I made a mistake there. It was the triangle. So I had to halve it. Very good. So we know that the height is 0.45. Excellent, Tiani. You're keeping me on my toes. So 0.45 is where we want to end up. So under acceleration due to gravity, I'm going to need to finish now, Tiani. We're going to have a curve here, and it's going to curve up to that point over there. Is that clear?
Yeah.
Okay.
Yeah, that's clear, sir.
Now the last question, very quickly. It asks you, is the collision elastic or inelastic? It has to be inelastic because the velocity is decreased. Kinetic energy is not conserved.
Yeah.
Tiani, thank you so much. We will give you a call later to get that other question that you want, and we'll chat to you soon. Okay, thank you so much.
Thank
All the
you.
best. Bye. Right, we're going to a short break, and we'll get on to another question straight after the break. Bye for now. Great to be back with you. We're going straight into a really interesting question, but we've had a couple of people ask this question, but we haven't been able to get them on the phone. So please, if you do leave us a message to call you back, please make sure you keep your phones on. We don't want to call you back and not find that you're at home. But I think this is a great question. It comes from a prelim paper. We do have the Gauteng prelim paper, so if you want questions from that, we can answer those as well. So let's go to this particular question, and what it is question number 3 from the Gauteng prelim. Let's just write it down and make sure that we've got it. So it's question 3, the Gauteng 2010 prelim. So if you haven't seen this question, I'm going to give you some time just to think about it and to have a look at it. It says the following. It says a small brick of mass 700 grams is projected downwards vertically. So it's vertically downward. So similar to the ball that was dropped. Okay, and with the velocity, its initial velocity is equal to 1,25 meters per second. Right, it's on the top of a building, and the height of the building, the height that it was dropped from or was thrown down was 25 meters. And what we're asked to do is to calculate the magnitude of the velocity. We want to find, first of all, the final velocity when the ball comes to rest. Calculate the magnitude of the velocity at which the brick hits the ground. So that's it, when it hits the ground. So when it hits the ground. Now, this one is giveaway. It's not difficult, but I just want to go over it. Remember that when you're dealing with these questions, you take out the information, draw a little sketch, and I'm going to do just that so that we've got a very clear picture of it. There's the building. It's 25 meters high. So up to there is 25 meters. The initial velocity over here was given as 1,25 meters per second. And we want to find the final velocity over there. Okay? Now, we're not given time, so we're going to need to think a little bit carefully. So what do we know when anything is thrown up or thrown down in the atmosphere? You should know at this point that anything that is thrown up or thrown down has to experience acceleration due to gravity. And the acceleration due to gravity is a value of g, 9,8 meters per second to the -2, and it's downwards. Okay, so let's do a sign convention and make sure that we've got this very clear. What's going to be our up and our down? What's going to be positive and negative? And for this question, I'm going to choose the down value as positive. So I'm going to highlight that and say that the down value is positive. We make sure that we've got that down value, write it in, we'll take down to be positive. So I'm going to write that again in my answer. I'm going to say let down be positive. Right, now I know the initial velocity, I know the change in position. Look, I know that the height of the building is 25 meters. So I know that, and I know that the acceleration due to gravity is 9,8 meters per second. You might be saying, but what about this value of mass? It doesn't matter if it was 6 grams, 700 grams, 7,000 grams, 1,000,000 grams, it doesn't matter. The acceleration due to gravity in the absence of friction is not going to change, is going to be constant. Mass has no change on the acceleration. It's only air resistance that could affect the acceleration due to gravity. If it's a very flat object, even if it was very light and it had a big surface area, it might slow down and might not accelerate at 9,8 meters per second downwards. But the mass, if we're ignoring air friction, then it's not going to make a difference. So let's go to fill in the answer here. What we've got is we've got the equation that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in y. Please note that we write the equation down as it is on the data sheet, use a and use delta y because it's a vertical process. We don't know what the final velocity is. That's what we're trying to find. Final velocity squared. Remember, when you see a square, you must take careful note of it and be very careful about it. Right, what's the initial velocity? We were told it was 1,25 meters per second, and it was downwards. It's positive. We need to square that. Plus 2 times the acceleration. It's also going to be positive because we've chosen down as positive, and the change in position is positive 25, so I'll put it in over there. Right, let's get the calculator up. It seems to have disappeared again. Just give me a second to get that calculator. It's over here, and I will get it for you in a second. While we're waiting for it, there it comes. I just need to close that. let's put in those details. So we want 1.25 and we want to square that. So that's the square plus 2 times 9.8 times 25, and we're going to say that is equal to this number here, 491,56, but we're going to have to do something to that. Please remember it said velocity, final velocity squared. So we must undo the square. We must take the square root. And in this case, we're looking for the positive square root. So we're going to say, let's just take this, and we're going to say answer, or sorry, clear. We're going to say square root, and then we're going to say answer, and we're going to say equal, and we get an answer that the final velocity is 22,17 meters per second downwards. So the final velocity, not squared now, we've square rooted this value, is equal to 22,17. Let's just pick up that value again and make sure that we've got it. Remember, give your answer to 2 decimal places. Look at the third decimal place there, it's a 1, so we don't change the 7. I was correct in doing that, like that, 22,17 meters per second to the minus 1. And remember to say that it's down. Okay, so that's the first part of the question. Now the next thing that we're going to do just quickly is do the next part, because that's where the interesting part comes in. It says the following. It says, on reaching the ground, the brick, this is what happens to the brick. The brick penetrates a distance of delta y equal to 10 centimeters into the ground. 10 centimeters into the ground before it comes to rest. And remember, rest, final velocity is 0. Okay? So this part, 3.2, says calculate the net work done on the brick while moving into the ground, while penetrating the ground. Okay. Right, so that's really important. Let's see how we're going to do this. There's more than one way to do this. Now, I'm going to revise with you very quickly the important theorem that we use here called the work energy theorem. So let's go to that. We're going to try and use the work energy theorem to work this out. What we're going to say, we want net work is equal to the change in kinetic energy, EK. So let's write this out. We're going to need some space for it, so I'm going to go to a new page, and we'll pick up the values. That was the previous page. Let's go to a new one. We're going to say net work is equal to the change in kinetic energy, which is going to be the final kinetic energy, half mv squared final, minus the initial. But remember, this part of the initial and final is not what was done. This is only in the ground. Okay, it's only in the ground. So the initial here, which needs to be squared, is not what it was when it was dropped. It's when it actually hit the ground. So in this question, we've got 2 initials and 2 finals. The initial, when we dropped the ball in the air, was the initial of the overall. The final for that is the initial of the second part. So we calculated that value. Remember, we calculated over here. It was 22,17. So we're going to need to use that as the initial velocity. The final velocity is going to be 0. And we can substitute the values in now. But remember what I said just now. Units, SI units, 700 grams. Please change it to 0,7 kilograms. So I'm going to do that now. 0,7 kilograms. Final velocity 0. Now some of you are saying, Doesn't he know that 0 squared times anything is going to be 0? Yes, I do. But the examiner wants to see the physics that you're thinking, that you understand that rest means 0 velocity. So please put the value in. Make sure you write 0 in this substitution here. Minus a half times 0,7, and the initial velocity here is going to be the value that we looked at just now, 22,17 meters per second. So we know that this is going to be 0, and what we're going to do is work this out. So let's get the old calculator up. We must square that value. So let's do that. We're going to square it. We're going to say, let's multiply the squared answer by 0.7 multiplied by 0.5, and we'll get an answer which is equal to 172,046875 joules. That's what the calculator gives, but we must do to 2 decimal places. So we look at the 3rd decimal place, which is a 6, and we see, that's bigger than 5, so let's change this to 172,0,05. So I'm going to do that now. I'm going to say minus 172,05. Let's check it, make sure we've got it right. Correct. We're all correct with that. 172 minus 0.5. Okay, so the final answer is this, that we've got the net work done in terms of this, in terms of the change in kinetic energy, was equal to minus 172,05 joules. Now remember, a joule is a scalar quantity. The reason for that negative is it's been caused to slow down. It's work done against friction that's causing this to slow. The direction of the force and the direction of the motion are opposite. So that's why the negative is there. So in fact, we know that this is because it's being worked on. Okay, so it's not a closed system, there is friction acting on it, and so that's the net work done. Please make sure that you've got that very clear and that you've got it sorted out. Right, now we do have a need to go to a break, and we're going to get another question up, and I think Farella's going to be able to take you through that in a few seconds. So I'll see you just now. Bye for now.
Hi, afternoon. Welcome back. Do we have a call on the line? Google, are you there? Hello?
Hello.
Hi, Google 2.
Hi, how are you?
Hi, I'm fine, thanks. Hi, you've got a question. Hi, is a question 12 of the November?
Yes.
Okay, November 2009 paper.
Yes.
Okay, that's the electricity question. Is that right?
Yes.
Okay. Now, I'm going to quickly draw the circuit, and then from there we'll be able to solve it. Is it fine?
Yes, it's fine.
Okay. Now, if I understand it, you've got a 6 ohm volt there, and these are connected in parallel. Okay.
Yes.
Okay, and a 12 ohm volt there. Sorry, a 12 ohm resistor.
Yes.
They're all connected, and there's a battery there,
Yes.
and these are all connected like that to a 2 ohm like that resistor.
Mhm.
Is that okay?
Yes.
All right. I think we've got a switch there,
Yes.
and a voltmeter. Let's call that one
Yes.
V2. Okay.
Yes.
And we've got another voltmeter here. Let's call it V1. Okay.
Yes. I recall.
And we've got EMF, and we've got internal resistance.
Yes.
Okay. Google it. That is how it looks, isn't it?
Yes.
Okay, now, then let us solve the questions. Question 1, they want us to get the reading of V2 and V1, okay, when the switch S is open. Is that fine?
Yes.
Okay. Now, what do you think the reading of V1 will be?
I think the reading of V1 is going to be 12 volts.
Yes, it's going to be 12 volts. Why do you say so, Google it too?
Because it's the voltmeter which is over the
battery, isn't it?
over the battery. Yes.
Yes, and this circuit, in fact, is not connected, isn't it? It's not a complete
Yes.
circuit. Can you see that? Because switch
Yes.
S is open, okay? Now,
Yes.
V1 will then read 12 volts. How about the reading of V2?
I think it's going to be 0.
Why do you think it will be 0?
It's because the switch is open, there is no current flowing through.
Yes, but can you see that this voltmeter V2, it is as good as if it was connected across the battery as well? Can you see that?
Okay, yeah, because the switch is in.
Yeah, because
The switch is under it.
the switch there is open, okay? So
Yes.
V2
Yes.
will also read 12 volts, okay?
Yes.
All right. Now, let us go to the next question. What are we going to find out now in the next question?
What will the new reading on V2 be when switch S is now closed?
Okay. Now, let us close that switch. Now it's closed. Okay.
Yes.
What will be the reading of on V2 there? Google it, are you with me?
I think it's going to be the same as that of V1.
Will be the same as V1. Because
Yes.
now V1 is reading 9 volts, isn't it?
Yes.
So, now we close the switch S. Do you think the reading will also be 9 volts?
Yes.
Why?
I think it's going to be the same as that of V1.
Now, if you can check carefully, voltmeter number 2 is not connected to any resistor. So, its reading there will be 0.
Oh.
Okay? Because it's not connected
Yeah.
to anything. It's just a short-circuiting there. All right?
Okay.
So, that reading of V2 will be 0. Now, what is the next question there?
Mm-hmm.
The next question, they say, calculate the external resistance, isn't it?
Yes.
Okay. Now, the external resistance here, they are talking of the resistance outside there, not including the internal resistance of the battery. Okay.
Yes.
Now, this here is the internal resistance, and the one in blue, this one here, is the external. Okay.
Yes.
Now, let us calculate the total resistance. Check carefully here. The total resistance of the external.
Total. Okay.
All right. We've got 2 resistors in parallel, 12 and 6, okay?
Yes.
Let us first find the total resistance of the resistors in parallel, okay? So we'll have 1 over R parallel is equals to 1 over 12 plus 1 over 6.
1 over 6.
Is it fine?
Yes.
So this will be equals to
72 over 18, which is 4.
Why aren't we using 12?
I know that over 18, like I need it's going to be product over sum.
Oh, okay, yes. So
When you've got
what
two
would be the
resistors in
answer?
parallel, it's going to be 72 divided by 18, which is 4.
Okay, 3 over 4. Okay. Is it 3 over 4?
72?
Did you say 3 over 4?
No, I said 72 divided by 18.
Oh,
Which
okay.
is 4.
All right. So there it will be 3 over 12, isn't it?
It's
So that the
4.
RP will then be equals to 4 ohms. Google it too?
No. Hello.
Hello, are you
Is
with
it-
me?
Yeah, I'm listening.
Are you with me? though?
Okay, yeah. Yes.
Can you see that we're calculating 1 over RP here?
Mm-hmm.
Okay? And we got that as 3 over 12. Is that fine?
Yes. Yes.
Okay? And then don't forget to flip over the RP because we have been calculating 1 over RP. But we are looking for the
Okay.
RP.
Okay.
Is it fine now?
Yes, it's fine now.
So our resistance there is 4 ohms. Okay?
Yes.
So that is the
Yes.
external resistance. Is that the external resistance? Let's go
Yes.
up and check. No, we've got the 2 there. We've got the 2 ohm. Can you see that?
The one which is in
So
series
we'll,
with the-
so
with
we'll
the-
need to add that one because it's in series, isn't it? So our total
Yes.
resistance will be equals to 4 ohm
6
plus 2 ohm,
which is 6 ohms.
which is equals to 6 ohm. Okay?
Yes.
So this is the total resistance of the resistor, of the external resistance. Is that fine?
Yes.
Okay,
Yes.
let's move on now to the next question. What does the next question say?
Calculate the internal resistance R of the battery.
Oh, calculate the internal resistance R of the battery. Now, we are inside here. Do you remember where I said the internal?
Yes.
Okay. Now, we have got the 9 volts there, which is for the external, isn't it?
Yes.
Okay. So we need for the internal. Remember the formula? It says EMF is equals to IR plus IR.
Yes.
Are you fine with that one? Now,
Yes.
remember this IR here is the internal resistance, okay? Internal.
Yes. Plus the
And this other
Yes.
IR here is for the external circuit.
mm,
Is that fine? So it means that we'll
Yes.
need now to find what? The current. Okay?
yes. Yes.
Now, how do we find the current?
Current is equal to voltage over resistance.
Current R is equals to
V over I.
V over I, isn't it? So therefore, our current will be
9 over 6.
9 over 6,
6.
which is equals to
Which is equal to 3 over 2.
3 over 2, 1,5 amperes, isn't it?
Yes.
So
Yes.
this is the total current
Mm.
passing through the circuit. Let's go back there to our circuit. So the 1,5 is the total current passing through here,
Yes.
through the whole circuit. Are you happy with that?
Yes.
Okay. Now, we can use that to calculate the internal resistance R. Okay?
Mm-hmm.
Now, how can we do that?
We substitute in our formula R, the external resistance, the current, and the voltage.
So in this formula, we can substitute that, isn't it? Okay,
Yes.
let me just erase here because now we have calculated that. Okay. Now let us substitute all the values now. What is the EMF?
It's
EMF.
9.
No. If you check carefully, Google it too. When we started, there,
It's 12.
it's 12.
12.
Can you see that?
Also, when we are now going to that formula, we use the voltage, the EMF before current is flowing through.
Okay, now the EMF is 12, okay?
Yes.
There are two methods which I'm going to show you now here. Okay, Google it too. But let us start with
Yes.
this with this method here, and then later I will show you how you can calculate that internal resistance R. Okay.
Okay.
But the EMF is when, remember, this is when the current is not flowing. It is 12 volts, okay?
Okay.
Now, when the current is flowing, the current, remember, it will stay the same throughout, even in the internal resistance, in the battery here, throughout the circuit, it will be 1,5, okay?
Okay. Yeah.
So the external resistance, that one, the external voltage is 9, we're given that, plus the current here is 1,5, and we're asked to calculate R.
Okay.
Okay? So if you bring 9 to the left-hand side, 12 minus 9, it will be 3.
3.
So 3 is equals to 1,5 R. Okay? So what will be the R?
R is equal to 2.
R is equals to 2 ohms. Okay. Are you happy with that?
Yeah.
All right.
Okay.
Now, let us go back to the second method, which I said I'll show you. Now, remember here we are talking of the internal resistance of the battery here.
Yeah.
So we can also be able to calculate here, because in the beginning we had 12 volts. And then when we closed the switch, we had 9 volts.
9 volts.
Do you remember that? Now,
Yes.
what is the lost volts? I'm going to just
3.
create a space here so that we can be able to understand what's happening. So the lost volts here, I'm just going to call this lost volts, is equals to 3 volts, isn't it?
Yes.
So you can use these lost volts to find the internal resistance, which is IR. So the lost volts is 3, and the I is 1,5. Sorry, 1,5, and the R is there. So still, if you're using this formula, you will find that the internal resistance R is equals to 2 ohm. Are you happy with that?
Okay.
Okay.
Yeah.
So you could have actually have used that method as well to find the internal resistance of the battery. Okay.
Okay. Yeah.
All right then. But I will prefer you to use this formula. Why? Because you've got all the values there, and you'll never go wrong. With the EMF equals to 12, the external voltage, which is IR, is 9. Okay? It is actually given there as 9. However, you can also calculate that one. Why? Because the current is 1,6 and 1,5, and the external resistance is 6. So 1.5 here multiplied by 6, it will still give you that 9. Can you see that?
Yeah.
So there are many ways of solving that problem there.
Okay.
Okay, Google2, thank you very much. Please call again, 0861 058 262, and then we'll be taking your questions, or you can email us at info@learnextra.co.za. Thank you.
Hi, great to be back with you. We've had an amazing number of calls, and lots of them are on this particular question that I'm going to do right now. It's all about the work energy theorem and inclined planes. I'm not sure if you're going to see one like this tomorrow, but let's make sure that we've got it sorted out. Shamini's called in. She was one of the many that we've been able to get back to. Shamini, how are you doing? Hello?
Hello?
Can you hear me?
Yes.
Okay, good, Shamini. You wanted us to go through question 6 from the March 2010 paper, is that right?
Yes, yes.
Okay, let's have a look at it. Here it is. I've just copied it or taken a photograph of it to put it onto the smartboard. So here we go. Told a box with a mass of 60 kilograms starts from rest at a height h and slides down a rough slope that is 10 meters long. At an angle of 25 degrees with the horizontal. So that's where the 25 degrees is. It undergoes a constant acceleration of 2 meters per second while sliding down the slope. Notice it's got 10 meters to go down. So now the first thing is to state the work energy theorem. That's a practical thing that you should learn from your notes. Remember, work energy theorem basically says that the net work is equal to the change in kinetic energy, and I did one like that from the Gauteng prelim just before we had the break, and Farella did his question. So now the next part, 6.2, draw a free body diagram. This is the important part, to show all the forces acting on the cardboard box while it slides down the slope. So it's extremely important that we get this right. How we're going to start this is remember what a free body diagram. Can you tell me what a free body diagram is? Do I need to draw pretty artistic pictures, or what do I need to do? Shamini?
Yes.
What do I need to do for a free body diagram?
You need to draw the slope firstly.
Okay, so what we need to do is to show all the forces, okay? And
yes.
What we are going to do is to recognize that we can take the box and represent it as a dot.
Yes.
So there's the dot. So now what forces do we know that are definitely acting on this box, which we're going to...
Gravitational force.
Okay, so there's the gravitational force. And the gravitational force always acts vertically downwards.
Yes.
Okay, straight downwards like that. What's another force that acts on this box?
F normal.
Sorry? F normal. So I'm going to call this FG. And then I'm going to say F normal. And the normal force, remember, is at 90 degrees to the slope. I haven't drawn it very well, but we'll just put up with it at that point. That's the F normal. What other forces are there?
F applied.
In this case, what is the force applied? Because it told me that it starts at rest and it slides down. So what's the thing that's pulling it down?
Is a frictional force.
The frictional force, remember, frictional force always opposes motion. And the frictional force will therefore act parallel to the plane. Okay? So you've got one of them, but I still haven't got the force applied. I'm going to just put in the frictional force, which is acting parallel to the plane. So I'm going to say F friction, act up, because it stops it moving. It's acting opposite to the direction of motion. So what's the force applied? We still haven't answered that. Look at the box, it's sitting there, and it's going to move downwards like that. So what's causing it? Is somebody pushing it?
The displacement.
Okay. it's not. The surface would be covered by the normal force. What's the other thing that's pulling it down? We've got it here, but we just haven't broken it apart. And that's what I want you to understand. That we've written the force that's acting on the box straight downwards is the force due to gravity. Agree? But in fact, that force due to gravity can be broken up into two components. The one that acts at 90 degrees to the surface, in other words, opposite to the normal. Okay? Are you with me? Shanae? And there's one that acts parallel. So this is the force of gravity that's acting parallel to the slope. That's what's causing the box to move down. So we've got these two components of the force. The one is the force perpendicular, and it's the component of the weight of the box that's acting perpendicular to the surface. The surface was at that angle, and there's the gravitational force that's pulling it down. Gravity doesn't pull down in this direction, but a component of gravity pulls parallel to the surface. Does that make sense?
Yes.
Do you understand the difference between the force and a component?
Yes.
Okay, good. So understand as well that to get this force applied is we're going to take that theta value there. So what we need to know is that the normal force is actually going to cancel. This one and this one are equal. They're in opposite direction. So actually, there are only two forces that are acting on this body when we break it down. What we've got, and to that original answer just with those three forces won't be incorrect, but it would also not be incorrect to do the following. To say, listen, the forces that balance each other out, and we want to draw them, to get them clear for ourselves, is we can do this. We can say there's a frictional force that acts parallel to the surface, frictional force parallel, and there's the force of gravity that's parallel, the component of the gravitational force that's parallel. Okay, so those are really the forces that we're interested in terms of work being done on this box. So I want to get that very clear into your head. Okay, how are we going to calculate the FG parallel? You got any idea? Look, there's the angle theta, and we know that angle theta is 25 degrees. Because look at the question, the angle of inclination was 25, and you need to know that the angle of the component will be the same as the angle of inclination. Okay?
Okay.
Okay. We can go and show you how to prove it, but I don't think that's going to help you at this point of time. So let's go on to the part that you're really interested in. And that was this. Calculate the kinetic energy of the box using the equations of motion. So let's see what information we were given. We were told that it is going to achieve an acceleration of 2 meters per second while sliding down the box. So its initial velocity was 0. Final velocity, we don't know. We don't know what that is. And we are told that the acceleration through this time is 2 meters per second parallel. Is this easy? Are you clear about what we need to do? The change in position is 10. So what equation of motion are we going to do?
Vf squared equals Vi squared.
Excellent. V squared is equal to Vi squared plus 2a delta x. Okay? Substitute the values in the initial velocity, substitute in, even if it's 0, 2 times 2 times 10, and that's going to give me a final 2 times 2 is 4 times 10, a velocity squared of 40. So what's the velocity, final velocity? Square root of 40. Do you agree?
Yes.
So what I'm going to say, just going to clear that, and I'm going to say square root of 40. It's going to be just more than 6, less than 7, and it's given me a surd form, 6,32. Look at the third decimal place, 4, so it's 6,32. So we're going to put it in 6,32 meters per second, and we should say down the slope. That was at the bottom of the slope. So the direction of the velocity was down the slope. That's where it is, down over here. Okay, are you happy with that so far?
Yes.
Okay, what about the work done by the gravitational force? So the work done by the gravitational force, to get the work done, what we can do, oh, sorry, I didn't answer it fully. Look,
Yeah.
I said kinetic energy. So we've got
Kinetic energy.
yeah, what did I do? I just worked out the velocity squared. Do you
Yes.
agree? I mean the velocity. So what do I need to do to get kinetic energy? EK is equal to half mv final squared. You must speak up if I make a mistake. It's easy to make a mistake when you're doing. You've got to check it though, and that's what's important. Go back and check that you've got that you've answered the question. So what were we told? It's a 10 kilogram box. Have you got the question in front of you?
Yes.
Agree? That, oh no, 60 kilogram box. So let's substitute that 60 in there, and we're going to say v squared is 40. So that's 30 times 40. I think that comes to 120 joules. Am I right?
Yes.
30 times 40.
1,200.
Ah, thank you. See, I'm not using my calculator, and you're absolutely right. 1,200. Do you want me to check it just so that everyone can see? 30, which is 60, 30 is half of 60 times 40. I must stop rushing. 1,200. So we've got the number of joules, and now we're asked to do the next part of the question, which is the work done by the gravitational force. I can calculate the gravitational force, find the force, okay? That's the one way. Find the force and then use the special formula for work. Right, now remember we're asked to find the work done against gravity. So we want WG. This isn't straight down. It's on the slope. It's parallel to the slope because that's where the work is being done. Remember that we're needing components here. Now, work done is always the force times the displacement. So it's the force of gravity that is parallel to the slope times the change in position, which is delta x, times cos theta. Now, let's expand this FG a little bit further, and we're going to recognize that that FG is going to be mg times sine theta, where sine theta is the angle that we're needing to pay careful attention to, the angle of inclination, which we've got in the question, times the delta x times cos theta. So that's looking quite involved, but it's not too bad. So let's substitute in. We were given the mass, which was 60 kilograms, times 9,8, which is the acceleration due to gravity. The sine here is sine of 25. The delta x is the length of the slope. So that's going to be 10 meters. And in this case, we need to recognize that the force and the displacement are in the same direction. So cos theta here is 0 degrees. Now, having recognized that, we can plug that into the calculator, and quite quickly, if you use a calculator, you will find that you get the answer of 2,485 joules. Now, remember, this is the work done by gravity. That's the parallel component on the slope. It's not the net work. Let's go back to the question to make sure that we've answered it fully. So just take a step back. Right, we've got the work done due to gravity. The next part of the question is the interesting one. We're asked to the work done by the box by the frictional force using the work energy theorem. Now this is very important. We've got to make sure that we use the work energy theorem. So let's go to that page and make sure that we understand what work energy theorem is all about. We've done something similar to this earlier on. So remember what work energy theorem tells us. It tells us that the net work is equal to the change in kinetic energy. delta K. But what is net work made up of? Remember, we do a sketch earlier where we showed the components down parallel to the slope, and I just want to draw it over here as well. We've got the force that is parallel, the work that is parallel at least. Let's just make sure that we've got this clear. We've got the work that is parallel to the slope, the work due to gravity parallel, and now we've got the work that is of friction that is also parallel to the slope, but it's in the opposite direction. So net work is the addition of these two, but this one is in the opposite direction. This one's in the down the slope, this one's up the slope. So when we look at those, they're going to be of different sign because the forces are in different directions. So let's be clear about that. We can expand our expression over here for the net work. We're going to have two parts to it. We're going to have the work. Let's change the color so that we've got it. We've got the work that is due to gravity, that is parallel to the slope, plus the work that is of friction, and that's going to give you the change in kinetic energy. Now, we've just calculated the work that is parallel to the slope. It's over there, 2485. So I'm going to substitute that value in, 2485, plus the work due to friction is equal to the change in kinetic energy. Now, we calculated the change in kinetic energy earlier. You'll remember it's 1,200. Right, we'll substitute in the value for the work done against gravity parallel to the slope is 2485 joules. We don't know what the work done by friction is, but we do know that the change in kinetic energy, we've just worked it out, was 1,200 joules. Now, to find the work done by friction, we're just going to change the equation, subject of the equation, subtract 2485 from both sides, we get 1200 minus 2485, and that gives us a negative answer, which is very important. We must make sure that it's a negative answer here because it's done in the opposite direction to motion. It's done by friction, 1285 joules. Okay, so there we've got the work done by friction. Let's finish this question off by going back to the question to just check the next part of it. Here we go. We're asked to find the magnitude of the frictional force acting on the box. Now that shouldn't be too difficult. We've just worked out the work done. So we know the relationship between work and frictional force very clearly. So we recognize that if we've got the work done by friction, we recognize it's the frictional force times the change in position, and these two are in the same same direction, cos theta. At the moment, the direction actually is in the opposite direction, so let's just make sure we've got that sorted out. So what do we know? We know that this is minus 1285. We don't know the force of friction. We know the direction is down the slope, and that was 10 meters. Therefore, the cos theta here, the angle is not 0 but 180 degrees, which gives us a negative on this side. And that means that we can calculate that the frictional force is going to be, this is going to be minus 1, and that's going to be 10. If we divide that by minus 10, we're going to get a frictional force of 128,5 newtons, and that's going to be up the slope because that's the direction the friction is doing. Thank you so much. That was a really interesting question. I made a couple of slips, but remember, when you put down your answer, go back and check the question to see that you've answered the question fully, and make sure that you stay on top of going over components and going over using work energy. Thank you so much for your call, and we'll chat to you again soon. All the best for tomorrow.
Hi, welcome back. I've lost a caller, but fortunately he had given me the problem. He would like me to solve a Doppler effect problem coming from the 2009 March paper. So this is question number 7. So question 7 on the 2009 paper. Now, it's about a dolphin. I'll try to draw that. So we've got a dolphin, a fish, okay, which is moving towards a rock. So there is a rock there. Now, the fish is moving at a velocity of 20 meters per second towards the rock, and it's emitting a frequency of 20 kilohertz. Okay, and on the rock there is a detector which is detecting the sound coming from the dolphin there. And the distance between the dolphin and the rock, that distance there is 100 meters. Okay, now the question here is to calculate the frequency which the detector here will capture as the dolphin is going towards the rock. So this is our rock here, okay? And the other information we're given is that the speed of sound in water is 1,500 meters per second. So we're trying to solve now the frequency which the detector will register, okay? Now in this situation, the frequency will be equals to V divided by V. It will either be a plus or minus Vs Fs. Now, in this situation, I just want to talk about the plus and the minus. The minus is when the dolphin is going towards. So towards there, it is a minus. Towards, the dolphin moving towards the rock is a minus, and when the dolphin is moving away from the rock, it will be a plus. But in this particular question, the dolphin is moving towards the rock, so we're going to use a minus there. So in this case, we shall have V which is the speed of sound in water, V minus Vs Fs. Okay, now the speed of sound in water is 1,500 divided by 1,500 minus the speed of the dolphin, which is 20. Okay, that is given there. Let's go up. That is given there. All right, multiply by the frequency. Now, if you can check carefully, you must be careful here. The frequency is 20 kilohertz. So kilo means 1,000. So you have to convert the kilo into hertz. So this will be equals to 20,000 hertz. Okay, so that is what we are going to write there. So that will be 20,000 hertz. Okay. Now we shall need a calculator there. Let me bring up a calculator. Oh, there we are. So it will be 1,500. I have to put a bracket there. 1,500. Okay, divided by, pen bracket, 1,500 minus 20, close bracket, multiply by 20,000. Okay, so the answer which I got there is 20270. 20270.27 hertz. So this will be the frequency which will be detected by the detector which is on the rock. Now the second part of the question is asking now, if we are to go back there to the diagram, I said earlier that the question said between the dolphin and the dolphin is 100 meters away from the rock. Now, how about if now the distance between the dolphin and the rock is now 50 meters? So the distance now has been shortened to 50 meters. How will that have an effect on this frequency? Now, if you can check the formula does not even have any distance in it. So this frequency will still be detected even when the dolphin is 50 meters away from the rock. So we'll still have the same frequency of 20270.27 hertz. Okay, so that does not change. Okay, thank you very much. Please do call us on 0861 058 262, or you can email us at info@learnextra.co.za. We'll now take a short break and we shall be back. Thank you.
Hi everyone, great to be back with you. I just want to remind you about that question that I posed and challenged you about. Mechanics question from the QuizMax worksheet that's up available. Let me just remind you of what it's about, and then let's have a look and see what it's on here. On this platform, www.quizmax.net, you can get a whole lot of questions, just like this one. I gave it to you at the beginning of the show. A ball being thrown up and down, or being thrown down, vertically up and then falling down, and you had to decide what the correct answer was. Was it A, B, C, or D, given this value? Now, let's go through that and let's make sure that you've got the right answer. You do get feedback when you answer these questions on your mobile phone. It will tell you whether you've got the answer correct or not, and it will give you a little bit of an explanation. But let's go through this particular one just very quickly while we're waiting. We've got a caller that's waiting, but I want to finish this so we can give you another question to look at. So it says, after 4 seconds, it's a maximum height. We want to find out what the position is after 5 seconds. What's happening? So at maximum height, we know that the velocity is 0 meters per second at maximum height. The acceleration is always 9.8 meters per second downwards. And we said let's make down positive, so it's going to be always plus 9.8 meters per second. So for a multiple choice question, establish what we know. It's either that one or that one. Those are the only two possibilities that we've got going here. Now look what's happening. We've got the ball that's reached maximum velocity. It was going up. It's now coming down because 4 seconds it was at maximum. 5 seconds it's going to be coming down. So it's moved 1 second after it was 0. How much is it? What's the change in velocity? Well, what is the acceleration? 9.8 meters per second every second. So after 1 second, what's its velocity? 9.8 meters per second. That's right. And it's downwards. So the correct answer is B. Please go and check that out. Make sure you understand why the velocity is 9.8 meters per second and that it's downwards. Well, it was 0 when it was going up. We've said down is positive, so that's how we got it. Hope you've got that. Look out for another QuizMax question in a few seconds. Go onto the platform and you'll be able to answer lots of questions under different topics, and we'll take a look at those. Right, now I want to move on. I was halfway through a question on the Gauteng paper. The prelim paper for Gauteng, and we've had a number of calls. Julie was one of those people that called in, and I want to just make sure that we've answered her question, because there were, as I said, quite a few people wanting to go through this work energy question, which I had already started. So let's see if we've got Julie on the line, and we're about to get her on the line, and I will then carry on and complete this question with her. So I've done the first few parts. I just want to make sure that we've got some space to go through. Hi, Julie. We're glad that you phoned in, and you've got a question on the Gauteng prelim, question 3. Is that right?
Yeah.
Okay. Now, Julie, I did start that question, and I don't know if you were watching while I was doing that, but let me quickly just go through what I did so that we've got it clear. This was 3.1, and we worked out the final velocity of the brick to be 22 comma. Let's just highlight that. Using the equations of motion. Are you happy about that?
Yeah.
That's not a problem for you. Okay, good.
No. Yeah.
So then the second part, we were told that the brick penetrates a distance, vertical distance of 10 centimeters. Okay? And we were asked to calculate the net work done on the brick while penetrating. So I said that the easiest way is to use the work energy theorem, which I then have worked out over here. So I said, let's look at the final velocity. We recognize the final velocity is 0. The initial velocity we know is 22,17, and we worked out that we've got a negative net work. That doesn't surprise us because it was work done against the direction of motion. Are you okay with that?
Yeah.
Okay, so the next question said we wanted to calculate, that was the network. We want to calculate the magnitude of the frictional force exerted on the block. Are you with that?
Okay.
Is this where you're having your difficulty?
Yeah.
Okay, so we want F friction, and what we want to do is we want to say, well, if we know that F of friction is the only force, what are the forces acting on the block as it's slowing down? Well, gravity isn't having a huge effect at this point. Frictional force is actually the net force, because that's the thing that is causing it to decelerate, to change its velocity. Are you with that?
Okay.
Okay, so the net force is equal to the frictional force. So what we know is F net is equal to the resultant force, or the net force, times the change in position, delta x or delta y. In this case it's vertical, so I'll make that, and it's cos theta. Okay, are you with me?
Yeah.
So let's just draw a little sketch of this. So you've got it. There's the brick, and it had an initial velocity. Which direction is the force acting on it? The motion, I want to put the motion in one color. It is moving downwards. That's its velocity. Which direction is the force acting on it? That we're going to... Well, there's a force of gravity acting downwards, but once it's got to the earth, most of that force is not going to carry on. It does pull down a little bit. Okay, so let's just include it. And we're going to say there is a downward force just let me change the color. I want to put in the downward force due to gravity. And what else? What other force is there? There's the frictional force that is slowing it down. So the frictional force is really the big thing here, but let's work out what these are, and then we can see what we've got. What we're going to do is we'll come back to this picture. These two are going to balance each other out. Do you agree?
Yeah.
Well, they're going to cancel each other. One is down, one is up. We want to get the upward force. So let's work out the resultant, or the net force. The net force is the thing that's going to actually act overall on the object. So let's make sure that we've got that. The overall force is the net force, and it's not downwards. The net force is going to be upwards because we've got a negative there. So net force is going to be up. Friction is greater than gravity. Let's put that as net. So I'm going to work out the net force here. We know what net work is. I'm going to ignore this statement. Let me just take that statement off the board. And let's work it through fully. So even though it's very small. So let's work out F net. Do you understand that? We've got the F net. The W net. Sorry, we've got the W net. Do you agree? From here, W net. So we're going to take that one in. Minus, what was it? Minus 172, comma
0.5.
0.5 is equal to F net. We don't know what that is yet. The delta y, that was given as 10 centimeters. I'm going to write it as 10 times 10 to the minus 2. So it's in meters. Now, Julie, the question is, in which direction was the object moving? It was moving from the surface downwards. In which direction is the net force? Up or down?
Down.
But look, let's just see. It was moving downwards. It was originally moving downwards. Do you agree? If the force is in the same direction as the motion, what would happen to the velocity? It was 22,17, or if we look back, it was a value of 22, something. We calculated over here.
Yeah.
17, do you remember? So now, when it hits the ground, it carries on. It was 22. What's its final velocity? Is it
0.
speeding up? 0? Okay, good. So it's getting less. So it's not speeding up, it's slowing down. If it slows down, the net force must be in the opposite direction. It must be upwards.
Okay.
A force that accelerates will be in the same direction of the motion. The net force will be causing it to increase in velocity. But when the force is in the opposite direction, then we know that it is slowing it down. Are you with that?
Yeah.
Okay, so just look at that situation and let's just follow that through. So what we've got, that's why it's negative. So we're going to put that in. We also recognize here that the net force is in the opposite direction to the direction of motion. So what's the angle here? This angle theta. It's always confusing.
180.
180, excellent. I'm glad you've got that. When they're in the same direction, it is 0, but this is 180. So here we've got a situation that they're in opposite directions, and 180 gives you a value of what? Cos 180 degrees. Agree?
Yeah.
Okay, so now if we start to work all of this out, then cos 180 is minus 1. Agree?
Mm-hmm.
Are you with me? Let's put it into the calculator and
it's giving me negative 0.95.
Okay, so let's just do it right from the beginning. I'm wanting 10 centimeters is going to be 0.1 times cos 180. Cos 180 degrees equals, and you can see here the answer is minus 0.1. Okay, I just want to put that over there. So we've got F net times 0.1, and it's negative, is equal to minus 12705. So now what do we have to do? Can you see? We're going to divide by 0.1, and dividing by 0.1 is like multiplying by 10. Am I right?
Yeah.
So we're going to say F net is equal to 1720.5, and that is going to be newtons. Are we happy?
Mm-hmm.
Okay, good. I hope you've got that very clear, that this is a positive value, and the reason that it was positive is that it was going to be the net work, which is upwards. So we've got that sorted out. But that wasn't the question. What we needed to do was to find out what the frictional force was. So let's make sure that we've got this sorted out. What is the force due to gravity? The force due to gravity is going to be the mass times g. So let's add that in to the equation. The mass of the object was 700 grams, 0.7 times 9.8. So what have we got here? We've got the calculator again. Clear. 0.7 times 9.8 equals this value of 6. Oh, there it went. 6.86. 6.86. Hey? 6.86 newtons. And that was going to be a downward force. So what we want to do is we're saying the total force The net force is 172 upwards. This is downwards. This is down. So the force of friction, has to be 1720,5 plus 6,86. And when you add those two together, you get the frictional force. Plus 6,86, which equals that value of, oh, I've actually made a mistake. Sorry about that. Let's add them together properly. 1720.5 plus 6,86 equals this big answer, 1727,36. Okay, 1727,36, 27,36. And that's to 2 decimal places, and that's upwards. Okay, Julie,
Yeah.
are we okay? Right.
Yeah.
And unfortunately, we've run out of time. What was did you want to go through the momentum one as well?
No, it's fine. I can.
Okay,
do
you
that.
sorted out. I hope that helps you. Thank you for your call, and all the best for tomorrow. Welcome back, everyone. It's been great doing your mechanics questions, and we've got one more area of mechanics that I don't think we've answered any questions on tonight, and that's a very important area. It's all about the conservation of momentum. Pumi's phoned in with a question from the September prelim from the Gauteng province. Now, not all of you will have seen it, but it's a really nice question relating to conservation of momentum. Pumi, are you with me?
Yes.
How are you doing?
I'm good, and you?
Are you feeling good for tomorrow?
Yes, kind of.
Very good. Just relax, get lots of sleep tonight if you can, and let's make sure that you do as well as you can. Okay?
Okay. Yeah.
Okay. Now, you've phoned in about this prelim question, and I'm glad you're going over the prelim questions, because that's a really good way to do some learning. So you asked for question 6. Let's have a look at it. I'm going to read it so that the learners who haven't seen this get an idea of it. Space shuttle consisting of a rocket motor with a mass. Now, when I read the question, the first thing I do is I underline all the things that are given. A mass of 600 and a capsule with a mass of 280, while traveling in space at this speed relative to the Earth, releases its rocket motor. As a result, the capsule is projected in the opposite direction at a bigger speed relative to the Earth. So now the first thing is they ask you to state the principle of conservation of momentum. Next thing, calculate the speed of the rocket motor immediately after it's released from the capsule. And then they ask you the question, is this an elastic or inelastic, and you must support it with a calculation. Okay.
Yeah.
Okay.
Yeah.
Now, where is it that you're having problems? It can't be on the statement of the conservation of momentum. Come, give me, how would you state the law of conservation of momentum?
The total linear momentum.
Yes.
Of an isolated system remains constant in magnitude and direction.
Correct. So you're absolutely right. You've done it perfectly. We say the total linear momentum in an isolated system, linear
Yes.
P, and we must say in a closed system, isolated, system remains constant. And the way that we can write that down in the equation form, if we don't ask to state it like that, is we can say the total momentum, sigma p, okay, before the collision, before a collision, is equal to the total momentum, or the sum of the momenta, that means of all the bodies after the collision. And this is a small p. I've just written it rather badly. Okay, so we add up all the momentum. If you've got three bodies, total momentum before is equal to the sum of the total of all the momenta after. Okay, so we need to remember that. Okay, so now let's go to the question. Calculate the speed of the rocket motor immediately after it is released. So I like to, when I'm given a picture, given a problem like this, I like to draw a picture. And I like to draw before and after. It's like one of those weight loss pictures, you know, those diagrams for taking these fancy tablets. Well, let's draw a before and after picture. And what we've got is we've got two things. We've got the rocket section and we've got the capsule section. And I'm going to call that the capsule and this the rocket. And what I'm going to do is I'm going to put the masses on. This is a little, it's not a space shuttle, it's almost like a probe. 600 is the rocket motor and 280 is so the rocket motor is 6, what was it? Have you got it there, Pumi?
Yes.
Well, how much was the
rocket motor is a mass of 600 kilograms.
600 is the rocket motor, so that's the motor.
Yes. Yes.
And the capsule?
And the capsule has a mass of 280 kilograms.
280 kilograms, thank you. And what we're told is that they have the same initial velocity. Their initial relative to
6,800 meters per second.
Okay, 6,800 meters per second. And I'm going to say, let's make the initial direction to be positive. So initial is positive, okay? I know it's moving in space, and some people don't really understand about frames of reference, but really in terms of these questions that we've got here, it's how they move relative to one another. A frame of reference is how the observer sees the object. Is it moving left to right or up or down? Okay, so we do need to say which way it is and put it into that situation. So that's the before picture. Now what's the after picture? What does the after picture look like?
It says, as a result, the capsule is projected in the opposite direction at 7,300 meters per second.
Opposite direction to the motor. Okay, let's
in the opposite direction relative to the Earth.
Okay, as a result, okay. So let's just look. And a capsule with traveling in space, relative to the Earth, releases its rocket motor. As a result, the capsule is projected in the opposite direction, okay? So what we're going to find is the capsule, it was moving in that direction, it's now going to be moving in the opposite direction. So, and so that means the motor will carry on moving in that direction, okay? Are we clear about that? Doesn't really make sense in terms of the diagram that I've drawn, but they're moving. I think what we're really trying to say is the motor moves in the opposite direction. Doesn't matter. We can say if that's the positive direction, this is the negative, then that will still be the positive. We're just defining the direction. So the capsule moves opposite direction. This is the capsule, and this is the motor. They're moving in opposite directions now, but what we're told is that the velocity of the capsule is now what?
Negative. The velocity of the capsule is 7,300.
7,300.
Yes.
Okay.
Meters per second.
There we go, 7,300 meters per second, and we're going to put it in there. So meters per second, and it's in this direction, it's opposite to what it was. Okay.
Yeah.
So how are we going to set it up? We're going to say, let's find the initial momentum. We're going to find the initial momentum, and we're going to say the initial momentum of the rocket and the capsule, the total initial momentum is equal to the total final momentum. Okay, let's break that apart. I'm going to go to a new page. just so that we can put it in nicely, because it's now got a little bit. So we're going to say total initial momentum is equal to total momentum final. And the initial momentum is the momentum of the rocket plus the momentum of the capsule. And this is the initial, and this is the initial, and this is going to be equal to the final of the rocket plus the final of the capsule. Okay, I'm going to focus on this part first of all. So I'm going to say to you, let's work out the rocket, and we're going to say, well, the momentum of the rocket initially is the mass times the initial velocity, and that is equal to the mass of the rocket, I think, was 600. Am I right?
Yes.
And its initial velocity was?
6,800.
6,800. And this was the rocket. And then we go, the capsule was MVI, which was 280 times the same velocity. Agree? Yes. So we can add these two together. Let's get the calculator out and let's add the masses and then multiply. So we're going to say the mass of the momentum of the rocket and the capsule is going to be equal to, let's add the masses, mass of the rocket plus the mass of the capsule times the initial velocity. You with me?
Yes.
Okay, so we're going to say 600 plus 280 equals 880 times 6800. Was that right? 6,800.
800, yes.
So now I'm going to substitute my values in, and then I'll come and write it. So what I'm going to do is going to say the rocket was 600 plus 280 times 6 that, and the final answer was this value. Now it's quite easy to read it off that it's a big number, 5984. I sometimes like to put big numbers like this into exponential notation. So I put it into notation like that, and I can see that it's 5 times 9, 84 times 10 to the 6, okay, which is 598,000 meters per second. It's very big. So 5,984 times 10 to the 6. Okay, am I right? That's 5 million actually, not 508. So it's 5 million, okay? Are we with that? Meters per, and that's not meters per second, but kilograms meters per second.
Per second.
Okay, are we okay with that? So make sure your units are right. Don't make a mistake on your units. Okay, now what we need to do is we need to work out, we know what the final velocity is. At least we know what the final momentum is. Agree? Because the final is equal to the same. We know what that is. And
the final momentum.
Yeah, the system is the initial momentum we've worked out, and we now know that that is equal to the total momentum final.
Oh, yes.
Okay? Are you with that?
Yes.
Okay.
Yes.
So now let's break up the parts. What do we know as part of the final? We know that we have the rocket. And what we were given for the rocket? We weren't given anything for the rocket. Well, that's what we're trying to find.
Yes.
That's right, eh? We're trying to find, we want to find, look here, calculate the speed of the rocket motor. We know the speed of the capsule. So we're going to work with that. Sorry, wrong way. So let's go to here and let's make sure that we've got this. I'm going to need you to help me with the values now. So the rocket is what we have to try and find. So let's go to the capsule. The momentum of the capsule is equal to its mass of the capsule times the final velocity. The mass of the capsule was 280. Its final velocity was 7,200. 300.
Yes.
300. So let me work that out. But there's a thing here. It needs to be negative. Are you with me? Because it was opposite direction. So I'm going to store this one because we're going to use that just now. And I'm just going to put it over there, and then I'm going to clear. So I'm going to say 280 times 7300 equals, and I'm going to convert it to my scientific notation, which is 2,04 times 10 to the 6. 2,044 times 10 to the negative to the 6, and it must remember that's negative. So now, now remember, this is the equation that we've got. We've got P final is equal to P rocket plus P cap. Now we've got P final. Do you agree? What was P final? We put it in over here, 5998, and I'm going to keep to 2 decimal places even in scientific. So I'm going to say 598 times 10 to the 6. This one, P rocket, we don't know yet, plus P capsule, we know is negative. Substitute the negative, 0,4 times 10 to the 6. So now I can add to both sides and I can get what the P rocket is. Do you agree with that?
Yes.
So I'm going to take this value and add it to that value because I'm going to add to both sides. So I'm going to take that and I'm going to say plus 5.98. What was it? 98. So it's, let me just see.
5,984.
5,984. Let's just
Times
do
10.
5.984 times, exponent. Exponent, I don't want to do that. 5.984 exponent. 6 plus 2.044 exponent 6 equals, and in my answer in exponential form, it's 8,028. I'm going to round that off to just now. I'm going to round it off just now. So P of the rocket is equal to, can you see? I had it on the reading,
Yes.
8,028 times 10 to the 6. Now, what do we know about the rocket? We know that the mass of the rocket was
600.
So this is equal to the mass times the final velocity. We're going to divide that in. We're going to say 600 final velocity is equal to 8,028 times 10 to the 6. So if we want the final velocity, what are we going to do? We're going to divide this by 600. Are you with me?
Yes.
Divide by 600 equals 13380. So the final velocity, this is a bit messy, but I hope you can follow me. 13380, 13380 meters per second. Okay, great.
Yes.
Last thing that I need to ask you is the last question, and we've only got a minute to answer it. So very quickly, we've done the calculation. Is this question elastic or inelastic? How are we going to know? I can't do it now, but how would you work it out?
I'd say kinetic energy
Correct.
before the collision.
Yes, exactly. So you'd work out the total kinetic energy before, work out the total kinetic energy after, and check what the difference is. And you should be able to work out that without any problems. Okay?
Yes.
Well, thank you so much, Premi, for the call. We really enjoyed speaking to you. All the best for tomorrow. Go for it. I hope you get as close to the total as possible.
Hi, welcome back. Please do call us if you've got questions, 0861 058 and 262. I think we've got a caller on the line. Hello? Hello, can you hear me?
Hello?
Hi, can you hear me?
Hi, yes, I can hear you.
Okay. So you requested from March 2010, is that correct?
Yes,
Okay. And you said you need question 13.
yes, that's right.
Oh, okay. Now, let me just quickly try to draw it for the others to see what we are talking about here. And
Okay.
then we'll be able then to answer the question. I think it's 220 volts there. And then it's connected to the lamp with 100 watts. And as that one there is 60 watts. These are the household in the home. Okay. So that is the diagram, and that's our fuse.
Yes.
Okay. Now, the first question here, which you can call it 13.1, it says calculate the peak voltage of the source. Okay?
Okay.
Now, which formula do you think we're going to use here? V? Are you with me?
1 over R total.
V max divided by root 2. Do you have a formula sheet with you there?
No.
You don't have a formula sheet. You will need to open your textbook so that you can get all these formulas. Okay?
Okay.
Now, what is the voltage there given? Is 220, isn't it?
220.
Yes, we are looking for V max there, divided by root 2. Do you have a calculator there?
Yes, I do.
Okay. Can you then find V max there, maximum voltage, which is 200 multiplied by root 2?
Root 2.
Yes. What are you getting there as your answer?
311,13.
311, 13. Okay. And the unit is volts. All right. Are you happy with that?
Yes.
So that is the peak voltage of the source. Okay.
Okay.
The next question here, 13.2, it says, calculate the resistance of the 100 watts light bulb when operating at the optimal conditions. So, if we can go up to that diagram, you are then asked to calculate the resistance of this bulb here. All right. Now,
Okay.
which formula are we going to use? What is it which we are given? We are given power. What is the power there?
WP is equal to delta.
Hello?
I'm not sure.
You are not sure?
No.
Now, have you got the formula sheet in front of you now?
I'm looking for it.
You're still looking for it?
Yeah.
Oh, okay. Now, but if you can check carefully, I asked you what is the power of that. What does this measure? 100 watts. What are we talking about here?
Potential difference?
100 watts. What does that represent? Do you know? This 100 watts here. What do you make of it?
Is that the potential difference, or we calculating the
But the
total resistance?
But listen, the potential difference, we've just calculated it here, and the unit is V. Okay? So my question
Okay.
is, which physical quantity has got W watts as a unit? That watts.
Power.
Power, yes, you are right. Okay? So power here is 100 watts, isn't it?
Yes.
They're asking us to calculate the resistance, isn't it? So the resistance
Okay.
here is not given. We're going to calculate that resistance. What else have we got here? What is the peak voltage? Are we going to use the peak voltage here?
Yes.
Hello?
Hello?
Can you hear me?
Hello?
What is
No, you're breaking up.
Okay, sorry. What is V here?
We're calculating the resistance.
Yes, we are calculating that resistance. That's why we've put a question mark there, okay?
Okay.
Now what I'm trying to do here is to list all the given information. Okay? Are you with
Okay.
me?
Yes.
Okay? So, what is the potential difference given? There. Can you see that?
Yes.
220, isn't it?
220.
Yes, 220. That is our potential difference. Okay? Now,
Okay.
which formula are we then going to use, which has got power, resistance, and the potential difference there?
Potential difference.
Yeah, which formula are we going to use? So the formula must have all these three physical quantities. Must I help you there?
Yes.
So P is equals to V squared divided by R.
R.
Okay? Now, make sure that always when you solve problems of this nature, you first list down the given information. And then from there, you can then be able to select the formula from the formula sheet. Okay?
Okay.
All right. Have you got the formula sheet now?
Yes.
Okay, that's good. So let us then substitute the values. Power is 100. What is the potential difference there? 220
220.
divided by R.
R.
Okay. Can you help us now? Use your calculator to find what the value of R is.
$2.2.
What did you get?
2.2.
Sorry, I forgot to square there, sorry. Yeah, because that is V squared, okay?
Okay.
So 100 is equals to 220 squared divided by R. Can you be able to calculate what R is? Okay, let me bring the calculator as well. There we've got 220 squared divided by 100. What did you get? Did you get 484?
Yes.
Okay. So that is 484. Okay. And what is the unit? The unit is there for resistance?
What?
Are you going to leave the answer like that, or are you going to give it a unit?
No, give it a unit.
What is the unit of resistance?
Volt.
Volts? No, it's ohms. It's not volts, because we are calculating resistance. So the correct unit is ohm. Okay.
Yes.
Yes, you must be careful of that, because you might write wrong units and you'll get it wrong. Okay. Now,
Okay.
can we move on to the next question now?
Yes.
Now, it says an electric iron with a power rating of 2,200. So this question is 13.3. The power is 2,200 watts. It's now connected across AB. Now, let us go back to our diagram there and see where AB is. Now, we have got A here and B here. Okay? Now,
Okay.
if you connect an iron there of 2,200 watts, it will not be advisable to do that. Why?
because there's a 60 watts there, and it will have too many.
Okay. First of all, hello? Can we first calculate the current then? Okay. Now, we have got the power. We are given the power as 2,200 watts. Okay. I want to list everything which we've got. Okay.
Okay.
Potential difference there is 220 volts. The current is not known. So, which formula then are we going to use to calculate the current? Are you still there?
Haven't.
Check on the formula sheet there. The formula which has got power, VRMS, and current.
P average
Yes.
is equal to VRMS
It's equals to VRMS.
is equal to W. Is equal to V.
Multiplied by current. Yes,
Yeah.
because I said we need the one which will have power, the potential difference, and the current, isn't it?
Yes.
Okay. Now, let us calculate the current there. So the power is 2,200. The potential difference is 220 multiplied by I. Okay. What will be I there? Do you have a calculator?
Yes.
Yeah. Can you quickly calculate that?
10.
The answer is
10.
10, isn't it? Now, can you see that the iron is actually, if you are to connect the iron between A and B, it's actually using 10 amperes of current. And the fuse here is 10.
10.
So what's going to happen? There is a light here and there's an iron there. And the fuse is 10 amperes.
It's going to be a short circuit
Why will it be a short circuit?
because there's too much of current.
The current will be more than 10, isn't it? And hence,
Yeah.
the fuse here is going to blow, okay? And then the current will stop flowing, isn't it?
Yes.
So what we have done here is that from our calculations, we can see that the iron is actually, the iron here is actually drawing 10 amperes of current. And therefore, together with that light, okay, the current will exceed 10 amperes, and then from there, the fuse will then blow. Okay?
Sorry?
Did you get my explanation?
The last part?
Okay, listen. The iron here will draw 10 amperes, okay? The light here,
Okay.
10 amperes as well, okay? Like the whole circuit here will actually be more than 10 amperes. Are you with me?
Yes.
Then, however, our fuse here is a 10A fuse. So
Okay.
if we have got more than 10 amperes of current, then this fuse will blow.
Okay.
So that will blow, and hence we will not have current flowing through.
Okay.
Okay? Are you happy?
Yes.
Okay then. Thank you very much. Please, if you do
Thank you.
If you do have another question, please call us 0861 058 262, or you can email us at info@learnextra.co.za. Okay, thank you very much. Thank you.
Great, guys. I hope you've enjoyed us and you've been together with us for some time now. Remember that we're going to repeat some of the sections that we've broadcast during the day. So if there's some sections of the paper that you're not too sure of, stay tuned. Don't leave us when we leave the live broadcast. There is input from experts in the field, from various people telling you what to expect in the paper, questions on mechanics, wave, sound and light, and electricity. So stay tuned after the broadcast. We're coming in for our last question this evening, which is another electricity question. Papa's phoned us with a question from the March 2010 paper, question 11, and there are quite a few other people that have asked for it. So good evening, Papa. How are you doing?
I'm okay.
Okay, I'm going to have to rush this because it's not we're going to run out of time. So the first thing we're going to say, question 1.1, please remember your definitions. Learn your laws. Ohm's law, what does it state? It states that the current is directly proportional to the potential difference. The current passing through a conductor is directly proportional to the potential difference across the ends of a conductor at constant temperature. Have we got that?
Yeah, I got it.
Okay, so learn it. Make sure you can do your marks. You see, it's worth 2 marks. If you learn all your definitions, you're going to get between 10 and 15 marks. Not a problem, and you're halfway to getting a good result. So now the question is, question 11.2. How does the resistance of M, let's not move that. I want to just lock that down so it doesn't move again. Give me a second. Lock it in place. How does the resistance of M, this one, of the resistor, compare with the resistor there? Explain how you arrived at your answer. So let's go and look at the circuit. We've got 24 volts across the battery. When there's no switch, so that's a closed reading. We've got the ammeter reading here of the total current. That's the total current. And we've got this. This is the current in M. This is the current in M, is 1 amp. Are you with me?
Yeah, I'm with you.
So what happened to 2 amps? It got to this point. It's in parallel, and that's the parallel section. It divided over here. 1 amp went that way. How much must go through this one?
2 amps.
Now look, we've got a total of 2 amps over here. 2 amps.
Oh, I think.
In this part of the circuit. Are you with me? Look at this.
Yeah, I'm with you.
So this part of the circuit, all of this part through the battery, it's all 2 amps. So when it gets to here, 1 amp goes that way. How much must go between these 2 points here through N?
1.
1 amp. So what does that tell us? It tells us that the current divides equally. The only time that current will divide equally when resistors are in parallel is if the resistances are the same.
Same.
Okay, so the answer to this first part of the question, 11.2, is that the resistance of M is equal to the resistance of N, because the current is the same. We've got 1 amp over here. Total current is 1 amp, so the current has divided equally. Okay, the current divides equally when the resistors are the same. Now the big question is, if the EMF is equal to 17 volts, 17 volts, calculate the internal resistance of the battery. So now let's go to the formula sheet, and you will recognize EMF is equal to I times R external plus little r. Now let's see if we've got what we can use here. The reading on the battery is 14 volts when it's closed. Now the reading on the battery is going to be, and this is the other way of expressing it, it's IR plus I little r. So we were told that this is 17 volts. The total current is 2 amps. Are you with me so far? And we know that the volts in the external circuit is equal to IR, and that was the reading on the voltmeter when the switch was closed. And they told me that that was 14 volts. This is 14 volts when it's working, but the EMF is 17. So this is 14 volts. So are you with me? So I'm going to substitute here. 17, this is EMF. This is 14, and this is 2 times little r. Okay, so 17 minus 14 is going to give me 3 volts is equal to 2R. So therefore, R is equal to 1.5.
1.5
ohms. Okay.
Yeah.
Clear. Calculate the potential difference across N. Now, I know what the current is. I know what I'm not going to be able to finish this, I don't think, in the time I've got. I know the resistance of N. I know the resistance of N. R of N is 2 ohms. So to calculate potential difference is easy. V is equal to I times R. We know that I was 1, resistance is 2, so 2 volts. Okay.
Yeah.
Okay, so I've got that one sorted.
Yeah.
Calculate the resistance of Y. Now, here's the trick, Papa. We know that this potential difference across here, this potential difference, I'm going to use an eraser here, across the parallel branch is 2 volts. We've just calculated that. So put a voltmeter across there, it will be the same as across the resistor. So that's 2 volts. We know that the total is 14. Everything else, so the potential difference across here must add up to 14. So 2 volts plus what gives me 14? That must be 12 volts. Are you okay? So now I know the current. I know the current. I is 2 amps. I know the potential difference is 12 volts. And therefore, I can use Ohm's law. R is equal to V over I, which is 12 over 2, which is 6 ohms. Okay.
Yeah.
Great. So we've got that question out. I hope that's helped you. Please remember to apply Ohm's law. Break the circuit down. Make sure you understand what's in parallel, what's in series. Okay?
Yes, sir.
Yes, Papa.
Sir. Can I send a shout out?
Yeah, do a shout out. It's at the end of the show. Quickly, do one.
Yeah, can I send it? I'm sending a shout out to Tsirela Gomremena from Unit D.
Okay.
And Kumbuza, and
Great.
Kumbuza, my sister.
Okay, that's great. Thank you so much. I'm glad that all your friends are watching as well. Tell them to make sure that they do the best they can. We've got other programs coming up, life sciences, accounting, and make sure that you tune in for chemistry on Sunday. Now remember, you can also go to, thanks Papa, we're going to say goodbye to you there. Remember that we haven't got through all the questions, but remember you can go to Quizmax, and there are a whole lot of questions for you to try. Use Opera Mini on your cell phone. It doesn't cost a lot. A couple of cents every time you do a worksheet, and you'll get the benefit of a bank of questions with lots of feedback when we can't help you as on live right now. So I wish you the very best. I want to say thank you for calling in. Unfortunately, we couldn't get your questions, but hope that we've been able to answer some of your questions this evening. Again, thanks to everyone in the background, the production crew, and to the directors as well, and to Farilla, my friend, who's helped us with the presentation of this edition of Learn Extra Live. From me, John, bye for now.